Here we are at number 3. So what have we got? We've got, again, a strong acid, hydrobromic acid, and a strong base, sodium hydroxide. So we are going to dilute and then run them both through to see what is left over, essentially. So this guy here is going to be 50 250ths of 0.002 molarity, because again the 50 is going to go with the 200 to make 250. So it's going to be diluted from 50 to 250 in the instant before it reacts. So it's going to be 50 250ths of 0.002. So 50 divided by 250 times 0.002 gets you 0.0004 molarity of your acid. And then this guy over here is going to be 200 250ths of 0.001 molarity. So that's 200 250ths of 0.001 gets you 0.0008 molarity of the base. Now, they are not equal to each other, so it's definitely not a pH of 7, and it's pretty much obvious here that your base is more than your acid, so your pH should definitely be above 7 by the time that we're done. How are we going to do this? Well, we're going to take H positive plus OH negative is going to come over here to make H2O. I've got an I got a C, and I got an E that is here. So I got 0004 and 0008. And who cares? Because again, that is a liquid. Because water is a product, our K value here is a big number. 1 times 10 to the positive 14th here. So strong acids and strong bases react essentially 100%. Technically, it's not true. It's 99.9999 whatever percent. And we'll talk about that in a second. But essentially, they react 100%. So how far can this go? Well, the limiting reagent here is your acid that we talked about before. So the best that I can go is 0004 to be left with none, and then 0004 here. Because I have OH that is still remaining here, and I'll put it here in the purple, that 0004, I have more OH there. Then what I can do is I can take the negative log of that to get the POH. So the POH is going to be the negative log of 0.0004. And so the POH, 0004 and negative log, is 3.40. So the POH is 3.40, which means then that my pH is going to be a 10.6. Oh, that's there, 10.6 to 3 significant figures for our reaction that is there. Now, technically speaking, that is not a 0. That is technically a lie. But it's going to essentially be 0. It's just not going to be exactly 0, because we can't be at equilibrium and have something at 0. So should they ask, they're not going to, but should they ask what that number there is that we are looking at here in blue, should they ask what that number is, remember that you always have H positive times OH negative is equal to 1 times 10 to the negative 14th, and so the H positive times 0.0004 is equal to 1 times 10 to the negative 14th, or technically speaking, that number is going to be 1 times 10 to the negative 14th divided by 0.0004. That's going to be 2.5 times 10 to the negative 11th. So technically speaking, that number there is not 0. It's technically 2.5 times 10 to the negative 11th, which again is 0.123456789. 10, 25, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think that's right. 2.5 times 10 to the negative 11th for our answer there, which, again, relative to that number there is essentially 0, all right? It's not 0, but it's essentially 0. Just for the sake of argument, if you were to take 2.5 times 10 to the negative 11th and take the negative log of it, you get, oh, hey, no big shock there. The negative log of that number gets you a 10.6 pH. Because all of these things are interconnected by our pH square. So, if you have a problem like this, that's a strong acid, strong base problem, the first thing that you do is dilute it. The second thing you do is react it as far over as you can possibly react it. If there is anything left over, H or OH, you take the negative log of it to get the appropriate pH or pOH amount, and then you can run it through your pH square to get the other values should you want to.